Hey there, everybody. Welcome back. In this problem, we're doing LaGrange multipliers again. We're going to look for the least distance between a 0.3 space where x equals 3, y equals 4, and z equals 0. And we're going to find the shortest distance to the cone z squared equals x squared plus y squared. So the function we are trying to minimize, least would be minimizing, is the distance formula. And so the distance formula is normally d equals square root of x minus x naught squared plus y minus y naught squared plus z minus z naught squared. That's the normal distance formula, but I'm going to work on using d squared. Because if I can minimize d squared, I'm finding the same spot where d is minimized, and we can avoid working with the root that way. So let's do that. And the cone is where our constraint is. We're looking for the shortest distance to that. So we're going to use that for our x naught, y naught, and z naught kind of thing. No, sorry. X naught, y naught, z naught is our 3, 4, 0. My bad. Said that I got a little hasty. And we want it to go to some point x, y, z on the cone. That's our constraint. So we'll call that g. And I used z squared and I moved everything to the left side. So we have it all on one side. This will, again, like I said, avoid dealing with roots. So I take the gradient of f and I've got, which is this right here. I've got 2x minus 6, 2 times y minus 8, and then 2z. If we do the gradient of g, we get negative 2x, negative 2y, and positive 2z. And we'll slap on a scalar multiple of that. So I'm going to just go through and we're going to line up the I, J, and Ks. My I's will be A, my J's will be B, and my K's will be C. So if I do A, I need to equate 2x minus 6 to negative 2 lambda x. So I'm going to move the negative 2 lambda x to the other side by adding it to both sides. And over here, then I'm going to move the 6 over through addition. I'll have that on the right. On the left, I factor out the 2x that's common to both. And it leaves me with 1 plus lambda. So I'm going to have x times 1 plus lambda equals 3. I cannot, I repeat, this does not mean no. It does not mean x equals 3 or 1 plus lambda equals 3. No, you can only do that when the right side is 0. It's called the zero product rule. Don't do that. We can't say this. Okay, that's a little side excerpt. So if we look at doing B, R, J, I'm going to do the same thing. I moved it. I got 2y minus 8 equals negative 2 lambda y. We'll move everything to one side, and then I'm going to move all my y's to the left, my constants to the right, and I end up with when I divide by 2, I end up with y times 1 plus lambda equals 4. And again, same thing as we said here. We cannot say that each thing equals 4. It's only when the right side equals 0. Finally, we take a look at doing it with the z's. And you're going to see you get z times 1 minus lambda equals 0. Okay, so what are we going to do with that? These are messy, but C is not. So let's start with C. We can do the zero product rule on C, so we get either z equals 0 or lambda equals 1. And let's roll with both. Okay. Option 1, if z equals 0, we come up to our constraint function, and we've got negative x squared minus y squared equals 0. If you divide by negative 1, we've got x squared plus y squared equals 0. The only way the sum of 2 squares equals 0 is if they both equal 0. Because x squared is greater than or equal to 0. Y squared is greater than or equal to 0. They have to be 0 to end up, each 0 to end up to it. And z was 0 here also, so we're at the origin. X equals y equals z equals 0, the origin. The other option was lambda equals 1. Let's plug these in up here and see what we get for our values. Okay. So in option A, we've got x equals, I plug in 1, I've got 2x equals 3. So x equals 3/2. I plug it into B and I get 2y equals 4 or y equals 2. I've now got x and y, and we want to, it's got to lie on the constraint function. So we're going to take those, we're going to stick them into the constraint function and figure out what z is. And when we do that, we find out that z's got to equal plus or minus 5/2. Okay, so we've got 3 points. We've got 3 points to check. We've got the origin. We've got 3/2, 2, and positive 5/2, 3/2, 2, and negative 5/2. If we go through and evaluate these all at F, we will see the origin gives us a 25, and the other two give us 25/2. And we're looking for the minimum distance. So the shortest distance from 340, P340, to the cone, z squared equals x squared plus y squared. Our good old is got to be the shortest distance. The constraint function we were doing, f was d squared. So don't just go with the distances 25/2. We got to do the square root of it. D squared was 25/2. We take the square root. We've got 5 over the square root of 2, or 5√2/2. I'm going to leave it like that. I don't need to plug it into a calculator. Don't rely so much on your calculators. Okay? It's kind of embarrassing. And so we have the minimum distance. And that's it for LaGrange multipliers. We'll do more in class tomorrow. Peace.